Alhamdulillah. Standard enthalpy formation, latent enthalpy products minus reactants. Enthalpy products. So three y plus minus 339. Therefore, minus 1362 minus 339. Then do I get minus 303. Perfect is y. Therefore, scientific information of propane 1 is minus 303. Stable ultraviolet light is needed for this reaction to occur. Provides energy to break. Plus Cl free radical to form. I want to form one chloropropane, so I want free radical to be in the first carbon. CH2, CH2, CH3, from HCl. CH2, CH2, CH3 plus X of chlorine to form ClCH2, CH2, CH3 plus Cl dot. Chlorine free radical. Now, definition of the term electronegativity: the ability of an atom to attract the pair of electrons in a covalent bond. And this part provides energy to break covalent bond of chlorine, and then understanding I want to form one chloropropane, so the free radical's got to be on the first carbon, and then that's it. Ammonia reacts with one chloropropane to form propylamine. Name and outline mechanism for the reaction: nucleophilic substitution. Nucleophilic substitution. Now it is 5 marks. 1 mark for the nucleophilic substitution part. So the rest of this mechanism, so I've got methane, ethane, propane, 1 chloropropane, and I want to form propylamine. Now this mechanism is fairly simple. You just, like all the mechanisms, you just have to memorize them. or keep rewriting them, drawing them out till you know exactly what to do with any type of compound or yeah. So lone pair of electrons NH3, attach carbon partially positive, CCl bond breaks, we form C H H H CH2 CH2 NH3 plus and then another morning molecule, acid base, takes proton, goes here, and then finally you form your propylamine. And the amine group still has a lone pair of electrons, so it can act as a nucleophile. So yes, yeah, perfect. Question 2, suggest why student records the time to the nearest second. Oh, sorry. Yeah, to the nearest second, not to the nearest 0.01 second. Hard to judge to the nearest 0.01 second. Hard to judge to the nearest 0.01 second. Complete table 2. So it's going to be 1 over time, so 1 over 12. .0833. Hard to judge, and there is 0.01 second, 0.0833. Plot values of 1 over t against temperature. You just plot it. It's not really want to go through it. And obviously, if you've got anomalous results, you got an outlier, ignore it. Curved line of best fit, and you should get it like this. And you've got an outlier here, but obviously you're not going to go like that. You just keep it like that. Use the line of best fit to estimate time for cross to disappear at 40 degrees Celsius. So you go to 40, here, whatever that value is, 1 over that. So yeah, that's whatever it is. Varies depending on your graph. Suggest by considering products of reaction where small amounts are used. Well, I'm forming sodium thiosulfate and dilute hydrochloric acid. There we go. I'm forming sulfur dioxide. And that's all I need to say. I need to say SO2 is toxic. So my student chose to not carry out experiments at high temperatures in range 1 to 10 degrees Celsius. Reaction would take too long. Calculate percentage yield for method 1. Calculate percentage atom content for method 2. State importance. 6 marks. So alhamdulillah. Don't know why I keep checking the mic's on or off. Let me stop doing that. So method 1. One of them percentage yield for method 1. I know I form this much of methyl propanol. So basically all I'm going to do really is, that's the yield of it. I want to find out the percentage yield. Basically what I'm going to do is find out the moles of reactant moles, find out moles of the product moles, and then do the product moles over the reactant moles. That's what I'm going to do. So first things first, do moles and I know it tells me in the question I've got 1 gram of organic starting material. So 1 gram starting here, so 1 over 116, that's the moles of that. Then I know the moles of this methyl propanol, that's what I'm making, is going to be the mass of that, which is 552 milligrams, so 0.522 grams of its MR, which is 72. Then all I'm going to do that is this divided by this times by 100, and that gives me percentage yield. So 0.552 divided by 72 divided by 1 over 116 times by 100. Zero 0.552 divided by 72, 1 over 116 times by 100, 88.9%. So we can just say 89%. An important percentage yield. The idea of getting as much product as possible in the reaction, or efficient conversion of reactants to products. Oh yeah, and the percentage atom economy. Well, percentage atom economy is MR of desired products over MR or reactants times by 100. That's the formula, and we include the moles as well. But in this case, we're not going to include the moles, right? So percentage atom economy for method 2. Well, MR of desired product, methyl propanol. So it's going to be 72 over MR of all reactants. So 74 plus the H2O2, which is 16 plus 16, 32, plus 2 plus 2, 34, times by 100. And that will give you 66.7%. Importance of percentage atom economy. Idea of minimizing the amount of byproducts. So percentage yield, importance, idea of getting as much product as possible, efficient conversion of reactants to products, percentage atom economy, idea of minimizing the amount of byproducts. Explain why Penton 2 has a high boiling point than Pent 1E. Now, before I even jump into this question, I know I'm going to have to talk about intermolecular forces, so why don't I just spot which ones they are? Well, Penta 2 and the hydrogen bonds. Pent 1E van der Waals, VWs. And now I've set the footprint of exactly what I need to say. And it's very simple, these type of questions. You just need the key facts. So Penton 2 has stronger intermolecular forces. Penton 2 has hydrogen bonds. Pent 1E has van der Waals forces only, and that's really important because if you just say has van der Waals forces, yeah, but then why is that one? Because that could also have a hydrogen bond, but it doesn't. It only has van der Waals forces only. Penton 2 has stronger intermolecular forces. Penton 2 has hydrogen bond. Penton 1 has van der Waals forces only. State the region and condition for this reaction. Pent 1 is formed by elimination of water from Penton 2. The region, concentrated sulfuric acid, concentrated H2SO4, and condition hot, concentrated sulfuric acid. You could also say concentrated phosphoric acid, H3PO4, if you're wondering for the formula. But yeah, sulfuric acid, concentrated, most common one to say. So outline the mechanism. So I've got pent-1ene formed from elimination wall from pentane 2. So methane, ethane, propane, butane, pentane. Alhamdulillah. Pentane, and I've got a the alcohol, the OH. Well, it's actually like this: oxygen, a hydrogen, and it's got lone pair of electrons here, something like that. Then you've got your H plus, bonds to it. Then what happens is now the oxygen is positively charged, which makes complete sense. It's bonded to a H plus, is positive, it's taking that charge. So the oxygen is positively charged, and it's bonded to the other hydrogen as well, positive charge. Then from the middle, the carbon oxygen to here. Then what happens is you've got this, methane, ethane, propane, butane, pentane. Now, got carbocation here. And because I know I'm forming pent-1ene, if I was forming pent-2ene, then it would go here. But I'm forming pent-1ene, so either this way, yeah. And then you form pent-1ene. So let's see me check them right. CH3, CH2, CH2, CH, CH3, OH, oxygen lone pair of electron bonds, so H plus, perfect. Then CH3, CH2, CH2, CH, OH2, oxygen plus positive, middle of CO to the oxygen, CH3, and then yeah, and then you got CH3, CH2, CH2, CH positive carbocation, CH2, CH2, H. Now forms a double bond there. Perfect. Explain the differences between structural isomerism and stereoisomerism. Use example, show the compounds, molecular formulas. Exhibit stereoisomerism and the three types of structural isomerism. So stage 1, the difference between structural isomerism and stereoisomerism. So structural isomers, molecules with the same molecular formula but different structure, whereas stereo isomers equals molecules with same structural formula but different arrangement of atoms in space. And unfortunately, if you don't memorize the definition with these definitions, you wouldn't have got into the first stage, right? You wouldn't get those first couple of marks. Unfortunately, if you did memorize them, the easy marks, you just need to copy and paste it from your memory. So that's the differences between them. You just went through definitions. Then it says use examples, show this, and it can exhibit stereoisomerism. So stereo isomers, lack of rotation around carbon-carbon double bond, and then the structures of what? Well, C4H8, the structures of E and Z but2ene. Yeah. Stage 3, well then the structural isomers, the three types of structural isomerism. So we've got, I don't know what's going on here. So we've got the different carbon chains. We've got different carbon chains. We've got methylpropene and but1ene. The different position of functional group. For example, but1ene and but2ene, and different functional group cyclobutane and but-1ene, etc., etc. But-2ene cyclobutane. And this, stereoisomerism, structural isomerism, 3 types. It's not like it doesn't come up on the A-level papers. It does come up on the A-level papers. Obviously, paper 2, also probably paper 3 as well. And in A-level papers, they come more as like 1 markers. Draw the chain isomer or something instead of a 6 marker. But you can still have 6 marker. The only way to even these marks to be even accessible, you need to know the differences firstly. Then you need to know the different types, and then use C4H8 and then your application to C4H8. How they'll have different types of structural isomerism. Question 6, given equation showing structural forms of conversion chloroethene into polychloroethene. So chloroethene, I want to show a conversion. So now I've got ethene and I've got ClH here, and then all that's going to happen is that double bond goes to a single bond. That's all that's going to happen. This goes, and then you've got branches sticking out, and then you've got brackets like that. And you got your N on the outside. So we observe a bromine water is added to polychloroethene. Observation. So polychloroethene, well, what's happened? We've gone from a double bond to a single bond. So no reaction. No reaction. Because polymer is saturated. Saturated, meaning does not contain double bonds. Does not contain double bonds. Deduce the molecular formula DEHP. So plus size added. Why plus size added makes it more flexible, so we can get that mark. Makes it more flexible. The molecular formula, that's going to be a bit harder to work out, obviously. But yeah, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19, 20, 21, 22, 23. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. C24. Because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Perfect. C24H, count the hydrogens, H38, and the O, how many oxygens there are? 1, 2, 3, 4. C24H38O4, plus as added, makes it more flexible. Draw a skeletal formula of ethane dioic acid. So ethane dioic acid, so I've got, it's a dicarboxylic acid, that's the key part. So it's going to have the C double bond O, and it's also going to have the OH, right? So first things first, ethane. So could do it like this, and then I've got double bond O, HO here, then you've got your double bond O, OH here. And that'll obviously just represent the carbon ethane dioic acid, C double bond O, OH, COH, double bond O. Oh yeah, you could just do it like this. You don't need to do it like that kind of way. You can just do it like this. HOOH. But it's important, like these are opposites, so it's OH here and then HO here, showing that it's flipped around, right? 7.2 ethane acid is formed by the oxidation of ethane 1,2-diol, state suitable region and a condition for this reaction. So it's formed by the oxidation, dicarboxylic acid formed by the oxidation of a diol. So it's going to be acidified potassium dichromate. Acidified potassium dichromate 6, to be even more specific. Now that's not, I don't think that's the hard part. I think most students, including myself, would struggle with the condition. What's the condition? It's reflux, and you do need to remember that reflux. Question 7.3. Ethanoic acid reacts with excess sodium hydroxide from sodium ethanoate. Shouldn't mix this much of ethanoic acid with this much sodium hydroxide. Show that sodium hydroxide is in excess. Okay, these kind of questions are generally like easy to get a couple of marks on, but they're hard to get full marks on because you need to be then the wording after that. So most common thing, find out the moles, right? That's easy. And find out the moles of sodium hydroxide. Times by 0.200. Four times by 10 to the power minus 3 0.01. Show that sodium hydroxide is in excess. Yo, that's 0.004. So that's clearly in excess. But you can't just show by calculation. You need to then the wording part. That's again. So what I would say is that the amount of sodium hydroxide needed for the reaction is 0.008. So amount. Actually, better way of saying is amount of leftover NaOH needed for reaction. Leftover sodium hydroxide needed for reaction is, well, it's a 1 to 2 mole ratio, so it's going to be 4 times by 10 to the power minus 3. Sorry, 4 times by 10 to the power minus 3 times by 2, and then 0.01 minus 1, so it's 0.002. Yeah, you could just say that. Then it says calculate the mass of sodium ethane dioate that can be formed in this reaction. So what I'm going to use, therefore, is the number of moles, not the excess moles, because it tells me sodium hydroxide is excess. So therefore, I'm not going to use sodium hydroxide moles. I'm going to use the ethanoic moles. So that's 0.04. So therefore, the moles of sodium ethanoate is 0.004. I want to find out mass. Moles is mass over mR. Mass is going to be the moles times by the mR, which is 23 plus 23 plus 12 plus 12 plus 16 times by 4, which is 64. But that will give me the mass in grams, but I want it in milligrams, grams to milligrams, then I times it by 1,000. So I don't care about the excess moles. I'm not going to be using that. I'm going to be using normal moles, the moles of ethanoic acid. 0.004 times by 23 plus 23 plus 12 plus 12 plus 64. Then times my answer by 1,000, 536 milligrams. Perfect. That's 5 marks. Hydrogen catalyst can be made by reacting ethanol with steam in the presence of acid catalyst. Give an expression for Kc in its equilibrium. Now Kc square brackets. Now obviously this is AS level paper, so you don't need to worry about Kp. I'm pretty sure that's only A level paper, but it depends what year you're on. The products to power P over reactants to power R, what year you are in. If you're in year 12, year 1 or year 2, H2O. And even if you're in year 1, probably might as well look through KP, like look forward to it, since it's very similar to KC, just a special rule, curly brackets, and then there's a couple. Once you practice it enough, then you'll get it. So CO squared H24 CCH5OH H2O. And remember Kc square brackets. Its units, well, it's going to be moles per dm minus cubed to power 6 over moles per dm minus cubed squared. That cancels out to moles per dm minus cube to power 4, and then that simplifies to mole to power 4 dm to power minus 12. Calculate Kc, and it's giving us the moles. So Kc is concentration of carbon monoxide, 0.110, but the reason they've given me volume, I need to show divided by 0.750 squared times by hydrogen, 0.220 divided by 0.750 to power 4. And you need to be really careful for these chemistry questions, calculation questions, because you make one mistake and you could lose not even 1 mark, you could lose all the marks. Especially if it's more than 3 marks. Like a lot of these calculation questions I've seen 8 marker in the A level paper, yeah, etc. And then H2O 0.156 over 0.750. .66 times by 10 to the power minus 6. It doesn't ask me for the units, so that's perfectly fine. Wait, is it said 10 to the power 6? Ah, another silly mistake. I wrote 0.156 is 0.156. Yeah, 7.66 times by 10 to the power minus 3. Again, I probably would have lose a mark for that if it was a real exam. So 7.66 times by 10 to the power minus 3. Then it says the pressure was increased by reducing the volume of the constant temperature. I don't need to know that. All it tells me that pressure was increased. Okay, that's what I need to know. Predict the effect of increasing the pressure equilibrium yield of hydrogen. Now, so increasing the yield, increasing the pressure and equilibrium yield of hydrogen. So if I increase the pressure, equilibrium is going to shift. I'm going to count 1, 2 moles there, 6 moles. Equilibrium is going to shift to the side with fewer moles of gas. So here, so in hydrogen, it decreases. And then explanation, that's really where the big majority of marks goes to. And you need to be very specific. So, increasing the pressure. So equilibrium shifts to the side with fewer moles of gas. Left hand slide shifts backwards in direction to oppose the increase in pressure to decrease pressure. Equilibrium moves left slash in direction of reverse direction, backwards direction. Propose increase pressure to reduce pressure, and fuel moles on the left hand side. Fuel moles of gas left hand side. I basically said that, yeah. Shift to the side with fuel moles of gas the left hand side. And then final part, predict the effect of increasing the pressure on the value of Kc. This one, if you just memorize a simple fact, you could easily write down the answer immediately. No effect. Only temperature can affect the value of Kc. And it says predict the effect of increase in the pressure. Well, nothing, only temperature can. So if it said increase in the temperature, then I would go like, okay, well, I wouldn't be able to do that then because it's not telling me where the four directions endothermic, exothermic, but you get the point. No effect as increase in pressure, no effect, only temperature can affect the value of Kc. That's the end of section A.